Okay, hello, Dr. Shubhobrata Rudra. Hope you can see my screen. And let us start this meeting with whiteboard so everyone can use that. Okay, so let us start. What we are talking about today? We are supposed to have our solution of this problem which I gave to you. Here we can see that this problem, question number 7, let me start with that. Here you have two important things to note. One is only no neutral connection. Therefore, you can safely conclude that there will be no current which contains triplet harmonic can find a flow path in this problem. Why? Because as we know that triplet harmonics are unidirectional and therefore they must need a return path through ground. They cannot flow like the other positive or negative sequence harmonics or even fundamental 7th, 13th, all of them are positive sequence harmonics, and 5th, 11th, they are negative sequence harmonics. But the interesting fact is that whether they belongs to which sequence, I showed you in the class that whenever you add them, what you will have, suppose if I try to add that 5th harmonics or 7th harmonics, their sum at any time point will become 0, because just like the fundamental, they too maintain 120-degree phase shift from each other. However, in case of your uh, third harmonics, they do not maintain it, and therefore you will not be able to find any kind of cancellation due to sum of all the three phases. And you need to provide them a flow path. Well, with that note, what we'll have our only uh, two current type of current. One which will move the rotor in the forward direction, one with the backward direction. However, with that is some intuition, but let us try to find out what will happen when one phase is absent from this proof. See, in this proof, let me tell you a few things. Here, when suppose our B phase is completely absent. So when B phase is absent, what you can expect that these, they are not connected, right? So if these are not connected, then there will be no current, and accordingly you can drop the current flowing due to your B phase component. So this will be not be there. However, please note that when you have this, basically only two phases are present, things will become, we call it short circuiting. Although we have VA and VC, and this part is broken, that VV part, so we don't have any VV here. Therefore, the current what is flowing through that A phase is now flowing through our C phase, right? The only difference is that in general case, you have, they maintain a proper phase sequence, but now only thing we can write is that whatever current, if both the phase incoming currents are signed as positive, we can write IA is equal to minus IC. So they have completely lost any kind of phase shift what they earlier used to have. Generally, what we can expect that IA and IC will be 240 degree, like IC should lag IE by an angle of 240 degree. However, here we can have at max 180 degree things. So how to edit this equation? This equation will become clear. So here what you will have, see from where equation is coming. This 0 basically implies you are having right. So when you have this part will become absent, and that is why you get mu hm sine omega t x cap, and that has to be the case because AFS this is completely aligned with your y line or y axis. And as we know that MMF produced by field coil should be perpendicular to that field axis, coil axis. Therefore, the entire flux or entire things will be acting along x direction, and you have only x, no y. Coming to the next part, that is very interesting. This part is not present. Coming to this entire part will become absent. Sorry. Here, if we can scroll a little bit, right. Here, please note that what we will have this cos omega t minus 180 degree, and this one also minus 180 degree. Now, how this minus 0.5 is coming? This is basically due to your cosine of 240 degree, because the coil axis C dash is 240 degree away from A dash, right? This is our C dash coil axis. So if you try to measure, you will find that they are precisely 240 degree ahead. Here one thing is that a okay. So now if that is the case that A and C they are 240 degree apart, you have to take measure from this direction anti-clockwise. Now when you have this, what you will have here, this mu hm sine omega t minus 180 degree, that will be resulting you mu hm sine positive omega t x cap. So basically these two will be added and will give you 1.5 mu hm sine omega t x cap. Fair enough. That means here for A phase you are having an oscillatory in MMA. Together with C phase you get only along one along x cap direction, but that is clearly time varying. Unlike your three-phase rotating EMF, which is time invariant, here the magnitude of the EMF is time varying. What is happening to this gentleman? This will give you like that. You please check root 3 by 2 what magnitude it will results in. Mu hm So what you are having here, you are having XY kind of mixed things, and it is continuously, it is not rotating at all. It is continuously fixed. You don't have any constant variation in terms of x-axis, y-axis. But what you are having, the resultant is continuously oscillating. And in which axis the resultant is walking, we can think about that also. See this x, that is 1.5. Let me clear this one. In your x direction, you have 1.5 mu hm. In y direction, you have 1.15. So roughly, the resultant work between slightly tilted towards 1.5, but along this line, sometimes it becomes positive, sometimes it becomes negative. It is not rotating. It is a stationary one. And that gives you the solution of question number 7. Now, question number 8 already discussed. Let us come to question number 9. What is there in question number 9? What is the effect of rotating EMF and flux waves of a three-phase winding produced by balanced three-phase current if two of the three-phase connections are interchanged? This problem, already we have a solution of this one. Let me take you to the presentation where we can easily see the solution. If possible, you just go through this proof that reversing the direction of field rotation, and you will get this one. What we are talking about, that we are, if we may keep A phase connection unaltered, B and C phase will be reversed. So if we just put it, what we'll be getting, this is our expression. Now, what changes happen? Changes happen due to shift. You are having your IC here, IB here, here, IB here. You may want that how to figure out which one is IC, which one is IB, precisely due to this phase lag amount. We know C phase current lags A by an angle 240 degree and B phase current lags A phase current by an angle of 120 degree. Therefore, this is due to B, this is due to C. And accordingly, we have our expression. What we have here, that is pretty interesting, 1.5 mu hm sine omega t x cap plus 1.5 mu bm cosine omega t y cap. So the net magnetic field has a constant magnitude and rotates clockwise at the angular velocity omega. So earlier, if you can recall, or let me take you there for better clarity, you have a minus sign, right? So it was rotating in the counterclockwise manner. And when you have rotated it, you got something rotating in clockwise manner at an angular velocity of omega. All right. So that's the answer of question number 9. So 8 already discussed, although some people couldn't recollect whether it was discussed, but I discussed 8. So there is no need of discussing it. 10. In a balanced two-phase machine, two winding and displays 90 degree electrical. in the space and the current in two windings are phase displaced 90 electrical degree. For such a machine, carry out the process leading to an equation of the rotating MMF wave. Pretty simple. Just we need to follow the steps that we did for finding out the expression of rotating MMF for three-phase cases. Correct. If you are feeling clueless, let me help you by giving you some hints. Say, let us go here once again to this. In this proof, when you have two phase, what changes you should carry out? Here, it should be Bm sin omega t. Another phase is absent, two phase case. So the middleman is completely absent. Here, since you have a phase shift of 90 degree mentioned in the question, and also this should be in an angle of 90 degree. What you will have here, you will have Bmm sin omega t. Let us discard this entire part due to our second phase of current. Then you have minus 0.5 Bm sin. This 0.5 will not come here. What will come here? Here you will have 0. Why? Because who gives you this minus 0.5 precisely? This from cosine of cos cos 240 degree. If you evaluate this, cos 240 degree gives you minus 0.5. But now, instead of 240 degree, we have 90 degree. So cosine sorry. We have our cos 90 degree here. So therefore, the second phase current due to which you could expect something in x direction that becomes 0. And that has to be the case. Just try to understand what you have here. In a two-phase case, you have something, one coil that is placed in this direction. Say coil A and A dash, and another coil B, B dash. Correct? So for A dash, what you have? You have something acting in this direction of x vector that is precisely along the axis of B coil B. And similarly, for this coil B, you should have something working in the direction of Y, right? So this part gone. Now, what you should have here? You should have sine 90 degree. And this part is also sine omega t minus 90 degree. So that results you, the resultant one is Bm Bm uh, sine omega t x cap plus Bm cosine omega t y cap. Clear? And this expression is completely matching with the balanced three-phase case where you have 1.5 mu Bm sine omega t x cap and 1.5 mu Bm cosine omega t y cap. Here what you have? You have, uh, sorry, you should append mu with all the cases, because ultimately that gives you the MMA. So that, uh, okay, here probably we are doing with, so sorry, this one was fair, Bm cosine. So that gives you the resultant flux density, and that gives you the answer of question number 10. So that done. Question number 11, a 6-pole 60 hertz has a rotor winding with a total number of 138 series turns and a winding factor Kr. So it's all about rotor. The rotor length is 1.97 meter. The rotor radius is, okay. One thing I just want to apologize, because now you can see that it is almost 3:06 in the morning. So I'm feeling a bit tired. I'll share the remaining problem solution shortly. Okay. I wish you good luck in your exam.